Good afternoon, everybody. My name is Michele Esposto. I'm going to present the work that has been done during my PhD program over the past 3 years on fabrication, characterization, reliability of gallium nitride HEMTs for high power application. My advisor is Professor Alessandro Chini. Here is a brief overview of my talk. I'll introduce the gallium nitride-based HEMT structure and the standard technology, some innovative solution, a overview of on the power switching applications of such a device, and the theoretical model for power switching design and performance prediction. The gallium nitride HEMT is a field effect transistor. The advantage of this structure is the formation of a two-dimensional electron gas at an hetero interface AlGaN-GaN or AlGaN-GaN structure. The advantage is a very high mobility with very high charge density, and basically this structure exploits the high polarization charge of this material. The standard fabrication process starts usually with the ohmic contacts deposition, device isolation using chlorine dry etching, deposition of Schottky contact. Typical Schottky metals are nickel or tungsten. Then the silicon nitride passivation layer deposition for the DC to RF dispersion suppression, and then bond pad deposition. These are a few pictures of a real device. There are two source contacts, one drain, and the gate finger. We developed a standard technology in cooperation with the National Nanotech Lab in Lecce, and these are measurement results of such a standard device. The measurements have been carried out here in this department using DC and pulsed IV setup. Current DLTS for spectroscopy, and load and source pull measurement setup for the RF power. This is a typical IV showing both DC and pulsed component, pulsed in a drain leg measurement setup. And we can clearly see that the pulsed current level is higher than even higher than the DC one. This means that the DC to RF dispersion effect has been killed by silicon nitride deposition, and moreover, there is a self-heating effect reduction. So the load pull RF measurement in a load pull RF measurement setup, we got a saturated output power of 2.9 watt per millimeter. The measurement setup, the measurement conditions are reported. Then we tried to improve this technology. So many solutions have been reported in literature, like surface passivation, and we have seen that is effective for the DC to RF dispersion suppression, plus the field plate structure or the gate recessing technique. But not so many results are in literature about the Schottky contact improvement. So, of course, a higher Schottky barrier height, a threshold voltage stability, and low leakage current are properties that are needed for a improved GaN HEMT technology. So what we tried is the introduction of a innovative metal. Many innovative gate metals have been reported, such all these: iridium, palladium, molybdenum, platinum. What we tried is a copper gate GaN HEMT. So in literature, there were results reporting gate leakage current suppression, 2 orders of magnitude lower lower leakage current, higher Schottky barrier height, but at very interesting small signal parameters. But none of those works have reported large signal performance. So what we tried on a standard HEMT structure, the 2DG density around 6E12, using standard ohmic alloyed contacts, titanium, aluminum, nickel, gold, mesa isolation, and silicon nitride passivation, using on the same wafer either nickel, gold, nickel, or copper, nickel, and we compared the large signal performance. This is the experimental gate leakage current measurement. We can clearly see that the gate leakage has been successfully suppressed more than 4 orders of magnitude between nickel, gold, and copper, and even the Schottky barrier height seems to be higher for the copper gate device. Then, sorry, this is the DC and pulsed IV of both samples. On the left side, the nickel gold one, and on the right side, the copper one. This is the measurement, the bias conditions. These are the bias conditions. We can see that for the nickel gate one, there's no difference between DC and pulsed IV, but in the copper gate one, we found a huge amount of dispersion. These are the IV that we got in the pulsed setup. So it seems that some trapping phenomena are dominating the transient behavior, even in the drain leg setup that we use for the pulsed IV. And of course, the RF power is way lower for the copper gate. The nickel gate 1 gave 1.2 watt per millimeter of saturated output power, while the copper gate 1 gave us only 32 milliwatt per millimeter. So, but the passivation process was the same for both devices, and the absence of dispersion effects in the nickel gate device points toward a trapping phenomena that interests the gate intrinsic region of the device. So what we tried is an interface trap characterization using a pulsed or non-DC, non-static IDVGS measurement setup. This is the setup we used. The drain contact connected to a constant power supply at 3 volt through a 50 ohm resistor, applying this VGS waveform from 0 volt to negative voltage values. 0 volt in this kind of device means open channel condition. This is a depletion mode device. And what we got is a ID versus time transient like this. The current goes down suddenly for the nickel gate HEMT after applying that kind of signal on the gate, while the copper gate showed a very slow transient in the orders of tenths of seconds. And reporting all the data point, ID, VGS point, we can clearly see that there's no discrepancy between DC and pulse values for the nickel gate device, but for the copper gate device, there is a non-complete depletion of the channel, even for very low gate bias, and sort of modulation of this transient modulation based on the pulse width. So after that, we tried some device simulation that confirmed the presence of trapping phenomena in the intrinsic region of the device beneath the gate metal. The new topic is the power switching GaN HEMT. For RF application, this technology is already, in industrial stage, but not yet for the power switching applications. So we developed a power switching measurement setup just to be able to evaluate the power performance in hard switching condition using a DC-DC boost converter. This is a summary of the measurements, the typical measurements we carry out on our devices, DC and pulsed IV characteristics, off-state breakdown with a drain current of 1 milliamp per millimeter. In this case, the breakdown voltage was higher than 200 volts, so we have a compliance limited measurement. And measuring the output power and efficiency on wafer in this power switching measurement setup, we got at 2 megahertz efficiencies in the range of 55 to 65%, possibly due to this dynamic versus static on resistance increase while increasing the drain bias. But there are some limitations on this technology for the power switching applications. Main limitations are the normally off behavior. We need a normally off device for safety reason in hard switching. We want to have a gate leakage current suppression, and we have to deal with a lateral structure. Usually power devices are vertical devices. So the applied field, the applied voltage spread across a thick bulk material, but not in our case. In our case, we have a lateral device. Plus, we have to deal with some thermal dissipation issue due to the substrates. We can have GaN on sapphire and silicon carbide, but now seems very promising. Gallium nitride on silicon. So we have to take into account the thermal dissipation issues. So how to fix all these problems? We tried and we successfully got a normally off structure using the N polarity of the material. If you have your GaN crystal, a Wurtzite structure with gallium atoms on top or nitrogen atoms on top, you can get the gallium polarity or nitrogen polarity. And exploiting the nitrogen polarity of such material, we designed this structure. Here are the band diagrams, the energy band diagrams in the access region, the most top one, and we can see that the conduction band goes below the Fermi level, but below the gate, using a thick AlGaN layer on top, there is no 2DG, so there is no conduction. And this is the experimental IV we got. The threshold voltage, even very small, it's positive. So we're now trying to improve this structure to get a better, higher threshold voltage, and of course higher current and better device. For the gate leakage current suppression, we are trying now to introduce in our device an insulator layer using atomic layer deposition of aluminum oxide. This is a very promising technology. Even silicon is looking to this technology. It's very reliable, it's very easy, and it's mostly a CVD deposition method. And we already got very good current suppression on a MOSFET, very simple structure, MOSFET, GaN MOSFET. And we are going to introduce this kind of insulator in our HEMT, in a MOS HEMT, and try to make some power measurements. Plus, we developed a theoretical model for power switching design and performance prediction. Why we did this? Mostly because all the background we have is for RF devices. So we need to think about our devices in a new way. You have to look at our devices in a different way, looking at the power switching behavior. Plus, most of the power switching material, either material or devices, are compared using different figure of merits. But we don't care much about figure of merits. We want to have design rules. We want to have equation to be able to design our devices for the best performance. And the existing models were developed for silicon devices. But we have to deal with HEMT, that is a lateral structure. So we have to redesign the electric field distribution. Plus, we're working on GaN that has very high power density compared to silicon. So following this flow chart, we found some equations for all these parameters. The key point of this model is the introduction of a kind of back-off parameters. So what we want to say is this. You have your device that has a maximum drain current and a breakdown voltage. We say the power density may be too high for your device. So your operating IV points will step back from the maximum values by S. B off is VBR over S, and Imax, ion Imax using K. And in our model, we use this this current equation that has been developed by Professor Jaina and Professor Rajan, based on a phonon optical scattering analysis. So we got all the equations we need for our design. We want to know how to design the gate periphery and the gate to drain spacing. So of course we have material parameters, we have operating points, and we have these two new parameters. There is one more order of freedom in the device design. We tried an estimation of the conduction losses based on just the simple equation for the on-stage resistance, the current path from drain to source, and we got this expression. Again, material parameters and constants, operating points, and duty cycle, and this element here. Exactly the same for the switching losses, using this model This is the depleted region of the 2DG that goes from the drain side of the gate toward the drain as the drain voltage in off state increases. And this is the expression for the switching losses. Even here we have operating points, IV operating points, switching frequency, and constants and material parameters. So of course we can see as the frequency goes up, the switching losses go up. And we have this parameter, K, that we introduce in this model that will give us a good chance to match our device for the best performance. This is the overall total losses equation. And then, trying to estimate the power dissipation density, we got this equation. That is basically the ratio between the power dissipation over the area, the active area of the device, and again, constants and material parameters, but these two, K and S, will give us the way to improve the power performance, the efficiency. So here we have the first simulated scenario, off-state voltage of 500 volt, on-state current of 1.5 amp, and for 3 different 2DG density. These are the other parameters used in our simulation. As we can see, changing the value of K, that means changing the gate periphery based on the equation I showed earlier. We can get the maximum efficiency of 99.9, very impressive results, for these, using these values of LGD and WG. But if we look at the power dissipation density, we have this value, that it's very high, it's a very high value that can, it may compromise the reliability of the device. So then what we tried is, okay, let's plot the power dissipation density and see if we can really operate the device here for the best efficiency, or maybe increasing a bit the value of K or the gate periphery, or making the device larger. We can, of course, we'll reduce the efficiency, but we can get a more reasonable power dissipation density. This is the last simulated scenario. Changing the switching frequency, we can clearly see that the efficiency goes down as we found in the equation of the switching losses. And here we have switching frequencies from 1 megahertz to 5 megahertz. Of course, increasing the frequency, our efficiency is going down, but we can compensate this increase in losses by reducing the DC components in our switching system. So, in conclusion, we developed and tested a standard gallium nitride-based HEMT technology. We introduced copper as gate metal, trying to improve the standard GaN HEMT structure, but what we found is an interface trapping phenomena affecting the active region of the device, and this trapping phenomena have been confirmed by means of numerical simulation. What we have done next was develop a switching measurement setup for on-wafer performance evaluation, and then we tried to address some of the issues affecting the gallium nitride HEMT switching technology. So we introduced successfully introduce a normally off gallium nitride HEMT, and we studied MOS structure for gate current suppression. And then we developed a complete theoretical model that give us all the tools that can help us to design and implement a efficient power switching transistor. What I'm working on right now in these months is, of course, improving the normally off structure. We are now currently studying dielectric properties on either gate current suppression and mobility and transport phenomena, plus we are going to design very high periphery devices and, of course, measure high frequency, high power, or switching power out of these transistors. This ends my talk. First, I want to thank all of you for being here, for attend this talk, and of course I want to greatly acknowledge my advisor, Professor Keeney, and Professor Siddharth Rajan at the Ohio State University in the United States, where I spent my last year of PhD and where I'm currently holding a postdoc position. Postdoc from Friday on, Thursday on. And these are the projects that gave us money, and so gave us the chance to do what we have done, and hopefully will give us chance to improve and make new research and good research. These are my publications. Thank you for your attention.